Now, here we're going to take graphs, so function graphs, such as the ones I just reviewed, and show how to shift them left, right, up, and down. If you have a graph of a function y equals f of x, then if the graph of the function y equals f of x minus h plus k, where h and k are constants, that'll be the same graph, but it'll be shifted left, right, up, or down. For example, y equals absolute value of x. As mentioned before, its graph is in the form of a V shape. It's actually kind of a piecewise defined curve where it's y equals x for positive x and negative x for x less than or equal to 0. And it's a little inelegant because at x equals 0, it comes to a sharp point. And again, mathematicians don't like sharp points. It's another kind of discontinuity. But okay, y equals absolute of x plus k, that plus a k outside the absolute value sign. That'll shift the graph up or down. So this, for example, is the graph of y equals absolute value of x. This will be the graph of y equals absolute value of x plus 1. This will be the graph of y equals absolute value of x minus 1. Here's the graph of absolute value of x minus 2, absolute value of x plus 2. So y equals f of x plus k, with a plus k outside the f of x. It'll shift the graph up k units if k is positive, down if k is negative. Now, here we have y equals absolute value of x minus h, where the minus h is inside the absolute value sign. That'll shift the graph left or right. So here's y equals absolute value of x. Now here, watch out, y equals absolute value of x minus 1. Here the minus 1 delays it by 1 unit, so it moves it 1 unit to the right. Here's y equals absolute value of x minus 2. That delays it 2 units, so it's shifted 2 units to the right. Here's y equals absolute value of the quantity x plus 1. That advances the graph 1 unit, it shifts it to the left. Here's y equals absolute value of x plus 2. It shifts it 2 units to the left. So y equals f of the quantity x minus a. It'll shift the graph right h units if h is positive. So okay, that gives a delay of h. So if you put the two together, y equals f of x minus h, that plus k. It'll shift the graph right h units and up k units if h and k are both positive. Left and down if they aren't, if they're less than 0. And it's a little counterintuitive, I grant you. The plus k moves it up, but the minus h moves it right. So there's a kind of a barrier that somehow the plus and the minus make it different depending upon which side, whether it's inside or outside the function. So for example, here's y equals f of x. It's a graph of that. Here the graph of y equals f of x minus h, that plus k, is shifted h units right and q units up like this. Now here's a matter of multiplying a function outside or inside. Y equals a times f of x, so multiplication outside the function. That'll stretch, squeeze, or flip the graph vertically. That'll make it taller or shorter or flip it upside down, up or down. If a is bigger than 1, then it's a vertical stretch. If a is between 0 and 1, then it's a vertical squeeze. And if a is less than 0, it flips up and down. So for example, if this is the graph of y equals f of x, then y equals 2f of x is twice as tall. Y equals a half f of x is half as tall, and y equals negative f of x is flipped up or down. So multiplying f outside by modulates the amplitude, which is amplitude meaning the height of the graph. Now we'll say a lot more about this later when we get to modifying sine and cosine function graphs. However, yes, amplitude modulation. That should sound familiar, does it? You ever heard of amplitude modulation? You have, actually. Anyone?
Yes.
How? Where?
I
When?
think of it like when you're turning music up or down
Well,
is kind of what I was thinking, but it could be something else.
you have a point. That's not bad, actually.
Or
Yeah.
strumming strings on a guitar. Is
Um,
that,
maybe. I mean, if you strum hard or low or softly, yes, that does
yeah.
indeed modulate the amplitude of the sound. But you know, if it's you're turning on a radio, is it AM or FM radio?
Yeah.
AM means amplitude
Okay.
modulation, you see. When you, it works by the radio tower emits a carrier wave, whose
Yeah.
amplitude gets higher or lower in order to in accordance with the amplitude of the sound wave it's sending. And of course, the sound wave is generally many orders of magnitude lower frequency than the radio wave. Now, the problem with AM radio is that when it's temporarily at a low amplitude, then the signal can be corrupted by random noise, lightning strikes, people switching on their cars, turning on their washing machines, what have you. All those give a little bit of magnetic static that can interfere with an AM signal. That's why AM radio is generally for signals that can take a bit of static. Morse code to the extent that still exists, or voice broadcasts, but not music. That's for frequency.
FM.
Exactly. And
Okay.
that's what happens when you're multiplying inside the function, f of the quantity bx, where the multiplication is inside the function. That will stretch or squeeze or flip the graph horizontally. If b is bigger than 1, then okay, just how adding inside the function has a reverse effect than adding outside the function. Here, multiplying by a number bigger than 1 will make a horizontal squeeze. If it's between 0 and 1, it's a horizontal stretch. It makes it move through its range more slowly. If b is less than 0, then it flips the graph left for right. So for example, here's f of x, the graph, and f of 2x runs through its graph range twice as fast, so it's squeezed horizontally, whereas f of a half x is stretched out like that. And f of negative x is flipped left for right. So this f of bx, the b multiplication by b, modulates the frequency as an FM radio. There, the radio tower puts out a radio wave of constant amplitude, but its frequency squeezes and stretches and squeezes in accordance with the sound wave it's transmitting. Now, the advantage of FM radio is that it's never really low amplitude, so it's not as vulnerable to static, and that's why they send music broadcasts on FM. The disadvantage is that it's not on a single frequency, but it requires to be broadcast on a range of frequencies called bandwidth. And therefore, there's only so much, and there's only so much bandwidth on the radio frequency spectrum. So the FCC has to allocate them, auction them off, or however they allocate them. Here's a graph of y equals f of x. If we do y equals minus f of x, that flips it up for down. If you have y equals f of minus x, that flips it left for right. And if you do both, minus f of minus x, that's a flipped left for right and up for down, which is the same as a 180-degree rotation. So for example, let's graph y equals the square of x minus 3. Okay, y equals x squared has this U-shaped parabola graph. X minus 3 moves it to the right 3. So here's the parabola graph moved 3 units to the right. Y equals 1 over x plus 4. Well, 1 over x has this hyperbola graph. The plus 4 moves it up 4. So instead of approaching 0 near infinity, it approaches 4 near infinity. Here, let's graph y equals minus of the cube of x minus 2. We start with x cubed, this n-shaped graph. Minus x cubed flips up or down, so this is more of an S-shaped graph. And the minus 2 inside means you move it right 2, so you have this n-shaped graph move to the right 2. It's going, instead of going through 0 by 0, it goes through 2 by 0. Now here the book gave an example. Here's this kind of jagged graph going from -5 to 0 to -2 by 3 to 2 by -3 to 5 by 0. Here they asked the graph y f of negative x plus 3, and b is that graph y equals -2 f of x plus 3. Okay, here's a graph of f of x. F of negative x is flipped left for right. Then adding 3 moves it up 3, so you get this graph here. For b, we take this and flip it upside down and stretch it twice as tall. So here's a graph of -2 f of x, and plus 3 adds 3 units. Okay, it's worth noting that this is evidently an odd function, so the f of negative x equals negative f of x. So flipping it left for right is the same as flipping it up for down. Okay. All right, we are done for now.